to what it is now. Then, the amount of oil that remains in the reservoir is related to the known volume drawn off from the wells, in the same way as the sample volume left in the tube is related to what has escaped from it to give the pressure drop. Years pass by. The underground pressure falls, and pumps must be installed to draw up the oil. But for years more, the crude will seep through the rocks far below to the foot of the boreholes, now outstepped across the field to tap its farthest confines. But at length, even pumping fails. Production stops. In former times, even though 2/3 of the field's oil still lay below, it was abandoned. Today, efficient production can sometimes be restored by applying pressure artificially, as by pumping water down into the oil-bearing layer to force oil again towards the boreholes. From a central station, water is pumped along radiating lines to the outer fringes of the field to exert the greatest useful pressure on the oil below. This artificial water drive is injected into the layer, forcing the oil towards the boreholes. Similarly, natural gas, separated from the oil, can be re-injected into the upper part of the layer, forcing the oil downwards. And in the laboratory, for examining these problems of secondary recovery, scientists have built a miniature oil field. The rock grains, found in a real layer, are replaced by irregular beads of glass, which become transparent when the cell is flushed with oil. Connections are checked. A graduated glass to measure output. Water, under force of gravity, enters the cell. If the oil is viscous, the more fluid water tends to bypass it and moves forward in irregular fingers. At first, oil alone is produced. But soon, though much oil remains trapped between the fingers, water is being produced with the oil at the outlet. This wastage can be reduced by lessening the oil's viscosity, for instance, by heating the reservoir. Hot water or steam generated in a central plant can be pumped under high pressure to wellheads where it is injected into the layer. This too can be verified on the laboratory model, where minutes of experiment represent years of applying heat to the underground reservoir. For it takes many years to heat up the great rock masses sufficiently to reduce the oil's viscosity to a point where the oil, bypassed by the simple artificial water drive, is finally forced towards the well and so becomes available. Still more drastic is the application of fire to the underground reservoir, the subject of this experiment. A plug of oil is ignited and artificially fed with air. This heats the neighboring oil and much reduces its viscosity, forcing it through the pore spaces towards the well. under ideal conditions, relatively little oil is burnt, and only dry rock is left behind. The task of the oil engineer is complex in its methods and tools. But in its aims, it is simple. To search the hidden depths of the world for new oil, so that proven reserves stay always ahead of increasing demand. And to husband the oil that is won, so that the greatest possible amount is available for the uses of mankind. The oilman not only develops, but conserves the unseen riches of the earth.